Okay, hi everyone. Welcome back to another session on advanced algorithms. Last time we discussed linear programming and how you can turn a relaxation of an integer linear program, which correspond to NP-hard problems like our good old fellow set cover, how you can transform these into an ordinary linear program without the integrality constraints, which then gives you in general, not an optimal feasible solution because it might be fractional. But then we consider two rounding schemes that still give you at least a set cover with a certain guaranteed quality. The simple rounding, where you just rounded deterministically, was an F approximation, and we found a randomized, almost log n approximation for set cover via randomized rounding, where you use the fractional solution as probabilities whether or not this set should be a part of the solution. One thing that was a bit unsatisfactory about, in particular, these two solutions was that you first have to solve this relaxed problem, the linear program, to optimality. Even though we know there are polytime algorithms for doing that, it's still relatively inefficient in practice, especially if you compare it to the two elementary methods that we started with, namely the greedy set cover method and the layering method that also yielded an F approximation. So you might ask whether it's really worth going through all the trouble of linear programming. The reason why the approaches we discussed last time are somewhat limited is that we didn't yet make the full use of the theory around linear programming. And what's been missing is the idea of dual LPs, dualization, and then in the end we will find that there's an approximation algorithm design principle based on this too that often avoids even solving one of the LPs. It just uses the two LPs as a design principle when making up the algorithm, but the LP itself doesn't really show up in the algorithm itself. So let's start with an example to introduce what dual LPs are. So if we have an ordinary LP, we usually call this the primal to just distinguish it from the dual that we will now construct. And the idea is this is a minimization problem. And in a sense, we know that every feasible solution that fulfills these two constraints gives us an upper bound for the optimal objective value, because we can just insert and compute what the bound is, and we know if that solution achieves a certain value, then we certainly can achieve this value, maybe a better one. Now it would be good to also have a lower bound on the objective value. So here an upper bound is kind of easy. You just have to find a feasible solution that attains this value. Well, if that's possible in the first place or not is another question. But conceptually, it's simple to prove an upper bound on the objective value of a minimization problem. But what if we would like to have a lower bound on the optimal objective value? Well, we would somehow like something that's smaller than this. So what we could do is we can start with this. And we can, so since the x's are all non-negative, if we make the coefficients smaller, we make the whole term smaller. So let's say we drop a few of the x1s, we drop a few more of the x2s, and we also drop a few of the x3s. Well, not really by coincidence, what I produced here is exactly the first of the two constraints. And we know for every feasible solution that this must be greater or equal to 10, because that was part of the feasibility constraints. So we found a lower bound on our objective value, namely 10. And just to reiterate, because the axes are non-negative, we can make the coefficients smaller and still obtain a bound in that direction. And we have to make them smaller in a creative way so that we match one of the constraints. Well, we could do the same thing with the other constraint. In this example, oh, it doesn't work because to go to the second constraint, we would have to make this a 2x2, and that doesn't work. It's not smaller. So with the second constraint, it doesn't work, but actually the lower bound that we would get is weaker anyway. So maybe 10 is the best we can do. Well, in this specific example, you notice that you can add up the two constraints. And what you then get is 6x1 plus x2 plus 2x3. And because we added up, that's greater or equals 16. Well, and if you just check coefficient-wise, then that's again a valid bound where we can make the line complete. So we actually found a better bound. Okay, and now you might have a guess how this can continue. In general, you can multiply each of the constraint with some variable, so multiply the whole thing, and of course then also the right-hand side. And you can add up the two, so you can build any linear combination. Well, not every combination works. We have to make sure that our y1 and y2 are non-negative, otherwise we invert weakly positive, I should say. I promised I would stick to weakly positive instead of non-negative. So we have to make them weakly positive, otherwise the inequality sign is flipped and we can't continue here. But apart from that, we can choose any multipliers y1 and y2 and add these two up. What we then find is that if everything works out fine, namely if this is really bounded by this, plus y2, 5x1, 2x2, oh sorry, this is just a minus, I copied it incorrectly. Well, and this we know is, okay, doesn't fit in that line. It's 10y1 plus 6y2. Now this here doesn't hold in general. If you pick the y's too large, it doesn't work. In fact, we can read off for every x a constraint on the y's. Okay. For x1, we have 5y1 and 1y1, and these two together must be less than 7. Okay, so what we get is y1 plus 5y2 must be less than 7. And we can read off the coefficients of the other two similarly. Minus y1 plus 2y2, just reading off here, must be less than 1. That's the coefficient of x2 here. And we get another one for x3, where we have 3y1 minus y2 less or equal 5. Okay, fine. For every such choice of the y's, we get one lower bound on our objective of the primal problem. Well, which lower bound would we like to have? The largest one. So we say we would like to maximize 10y1 plus 6y2 subject to these constraints. Well, and heck what? That's just another linear program. So indeed, we just found naturally a dual problem. I didn't want to re-erase the colors. So we found a dual problem that has essentially the same type of problem. It's also a linear program. It has max instead of min, and it has the inequalities flipped. But I claimed last time, even without a proof, that you can always transfer one to the other. For max and min, you just make a sign flip here. And for the inequalities, you can multiply by -1 and then also change just the coefficients. So in fact, this is the same, and one can show that the dual of this one is again the primal. So these are really just two LPs, and they correspond to each other in a very nice way. And I think this is the way you should remember how you dualize linear programs. You have the idea in mind that you multiply the constraints with certain dual variables so that you get the best bound on the objective you can achieve by that. In general, if you write down LPs in the vector matrix notation we introduced last time, then this is the primal in the standard form. And then if you go through these steps, you find that the dual actually can be very easily constructed from the primal by just having the matrix transposed and the two vectors exchanged. Now what's a bit hidden here is that you also, well, in this notation is not so nice. For every row here, you get a column here in a sense. So for every constraint in the primal, you get a variable in the dual, and vice versa. For every variable in the primal, you get a constraint in the dual. That's exactly how we constructed these. So if you would like, we can just write down one more time 7, 1, 5. That was the objective in that case. The B was 10, 6. And the matrix A in the primal was 1, -1, 3, 5, 2, -1. And here we have the dual problem. Let's move these a bit over here. And then if you just compare, B is 10, 6 as predicted, C is 7, 1, 5 as we wrote it down here, and A transposed is 1, 5, 1, 5, -1, 2, 3, -1. So this easily checks out. And this might be the version you can easily memorize superficially, but I guess this one sticks even better because you understand what's going on. Now you might wonder, if you have an LP that's not in standard form, do I have to transform it first to standard form? And the answer is, if you just want to dualize, essentially no. Because if you have, this is what we just had, if we have inequality constraints, we have constraint variables in the dual, because otherwise we would multiply an inequality with a negative number, so the sign would flip, or the inequality sign would go to the other direction. If we, however, have in the primal an equality constraint, which we in general can also allow, then the y that we obtain in the dual is unconstrained, because an equality can be multiplied in either direction. And these go back and forth because primal and dual, the dual again, the dual of the dual is a primal again. So if you start with a variable that's sign constrained, then its corresponding constraint must be one with an inequality. Whereas if you have a variable that's unconstrained, you must have an equality. You can think about it for a while, that this easily generalizes to that situation. Now here is just again formally stated that the cost of the primal is lower bounded by the cost of the dual, and this relation holds for any two feasible vectors. So whenever you have this, these constraints satisfied, and the proof is so simple that you can just write it here in basically one line. We start with CTX. Now, since x is greater or equal 0, and we know something about the C here. So here, we essentially use 1, but we transpose it first. So if you transpose both sides, you get ATX transpose, which is X transpose A. Less or equal C transpose. So if you read that the other side, it becomes a greater or equal. So, oh, this should be a Y. That's, sorry for that. Dual variables are always Y's. So then it's YTA X. Then we can group this here. And use the constraint of the primal to get YTB. And since these are just, this is just a scalar, the vector product of the two, you can also exchange them. So the proof is easy and just formally verifies our construction that it goes through in the general case, but it should not come as a big surprise given how we constructed the dual. The point is that there's a lot more behind dual LPs, and that's the following set of theorems. The most important one for us is essentially the strong duality theorem. If you have optimal vectors x and y for x star, y star for the primal and dual LP, and this implicitly assumes that these exist. So the first sentence deals with the case that an LP can actually be infeasible, so it doesn't allow any feasible solution just because the constraints contradict each other, or it could be unconstrained if you can make the solution better and better, then the dual is infeasible. But if neither of those happens, this is an if and only if. So there's a finite optimal vector for the primal if and only if there's one for the dual. And in this case, you can pick two optimal such values, and then their objective values are equal. So it's not only that we have these lower bounds, or that we can give some lower bounds on the objective value of an LP. We can actually compute it precisely by giving a good solution for the dual, an optimal. So this may sound not so surprising, even especially if you already had a course on linear programming or linear optimization. But in fact, what this shows is that the decision version of LPs, so given an LP, does it have a solution with objective value better than a given threshold? This problem is not only in NP, which is easy to see, because a yes certificate is just a feasible solution that achieves a value better than that. No, it's also in co-NP, because we can also give a no certificate by giving a feasible solution for the dual problem, so that we get a lower bound that's better than the threshold. And this is striking. From a complexity theoretic point of view, again, it's not surprising since we already knew that L is in P, so this implies that it's in NP and co-NP. But it actually gives us a very nice way to construct certificates, even if we do not solve the LP to optimality using simplex or whatever method. In general, for integer linear programs, this does not work. Weak duality still works. If you just take the dual of the relaxation, then the integer integrality constraints just restrict the region of feasibility more, so every integer solution is still feasible in the relaxation, and therefore weak duality follows. But strong duality in general does not hold, and we will see today also a concrete example where we make use of that. Then there's a second theorem that essentially falls out of strong duality. It's easy to prove, even though I will skip the proof because it's just filling with these matrix representations. But we will make use of this in algorithms. So I think it's very helpful to have this these complementary slackness conditions. So again, we pick two solutions that are feasible for the primal and dual, which implicitly assumes that none of the two problems is infeasible, so that we can find one. Then this pair together is optimal, meaning that x is optimal for the primal and y is optimal for the dual, if and only if these two conditions are satisfied. And these conditions essentially say that either the variable that we consider in the primal and the dual is 0, so the smallest value that it can have, so it's at the boundary in a sense, or it's constrained in the other problem. So if the variable is in the primal problem, then this constraint is in the dual, involving the dual variables, is fulfilled with equality. Remember, these were inequality constraints in the original formulation. And these complementary slackness conditions say either the variable is tied to its bound or its corresponding constraint is tied to the bound in an optimal solution. And this is an if and only if. This is really useful because it allows you to solve one problem to optimality and then construct the solution for the other in a certain sense. And it's also a good criterion to just easily check if we are given two solutions. This is very easy to compute, so that we can easily check if the two solutions are optimal. Of course, to check if the two are optimal, you could also just compute whether the objective values match, which is in a sense what we're doing, but these are algorithmically more useful. So let's come back to our favorite problem in this chapter, set cover. We've already seen last time the integer linear program that corresponds exactly to the set cover problem, and we've also seen the relaxation where we give up the integrality constraint. Now for this primal problem we can construct the dual problem. And remember, the objective here and the right hand sides of the constraints are just, they swap the roles. So in the dual we just maximize the sum of these variables, and we have constraints of this type where the costs of the sets show up. And remember this V of u, that was a notation we introduced for convenience. That's the set of all j's, of all indices, so that u is contained in this j set. So here you had a constraint for every element in the universe, and you said at least one of the sets that contains me must be selected, must be covered, or in the fractional case, greater or equal 1. And in the dual problem, you have one constraint for each of the sets, j in 1 to k. So remember, the input for set cover were these k sets, where each was a subset of the universe 1 to n. And we had these costs for the sets. Now here in the dual, we have a constraint for each of the sets that says if I add up the values that I assign to the universe elements and add these up for all the elements in my set, I should not be larger than the cost of this set. And we can now find, so this construction back and forth, that's just automatic, or just by rules. We have syntactic rules to convert one to the other. But what the helpful part is trying to find for this one, we know the intuition, it's a set cover problem. And now we can try to find an intuition for the dual that helps us to come up with an algorithm. And one intuition that you can have for the dual as it's given here is YU means you would like to use or take with you as much as possible of the good of type U, but you have constraints, namely sets of goods, so that if you combine the sets in the goods in this set, you must not exceed a certain capacity. And these are just expressed here. Okay. Now, as a first application of this, let's look at the greedy set cover algorithm again, under this new lens of duality. So here's the algorithm again. It's essentially the same. I just swapped a bit of the notation to be more consistent with how I used it in the LPs, because it's very well established in the world of LPs and dual LPs to use xj and yi. Here I used u actually because these have meanings for us. So I just to warn you, this is not a very literal copy, but essentially a literal copy of the algorithm we had before, just with a few renamings. Now this algorithm computes for each for each element of the universe a certain price. And this can be interpreted as one of these dual variables that have to fulfill certain conditions and so on. But what we see in the algorithm is, so let me write down, price of u is essentially a dual variable. It has certain meaning similar to our intuition for the primal. But in the way that we have it here, it's not really a solution because it's not feasible in the dual. And one reason how you easily can see that this can't work the way it is, if you sum up all the elements' prices, then just by construction, how we defined those, essentially we use the price of an element to charge the elements that we cover with a new set, to charge the cost for this new set to these elements. And we do so in a way that in the end, what we have is essentially the cost, is exactly the cost of the whole cover of the curly C that we return is distributed to all the elements. And we know that this is the objective of the primal. So if y was dual feasible, then our C was optimal, right? And that would be great, because then we would have solved to optimality an NP-complete problem. So maybe this is not the point. And well, you can also show that the y's don't fulfill the dual constraints in a specific example. What we will do instead is consider this lemma, because it's true that these are essentially the right ones, but you have to scale them. And you have to scale them by hn, which is again something you should remember. This is exactly the approximation ratio we achieve in the end. So maybe this is not super surprising that this is the outcome that we have in the end. Let me already add a page. So again, we call the elements E1 up to En. In the order they are added, or they are covered by our greedy algorithm. Okay, so we just rename them, reorder them to have a convenient naming. That's the same as we did before in the ad hoc proof that we have this approximation guarantee. Now consider any set of our sets that we can choose from, and assume it has exactly L elements. And consider the phase in the algorithm when EI was considered. So EI was the element that for which this was, EI is one of the elements that we now added with this. I forgot to rename one. This is a J. At some point in time, we added EJ because we added a new set, and EI was one of the elements that was not previously covered. So when this happened, this set Sj contains at least L minus I plus 1 uncovered elements. Well, simply because we have just added I minus 1 elements up to now. So maybe it's nicer to write it like this. We just have added I minus 1 elements and now add the ith. So there's just not more elements in the set C here up to this moment. And that means if we added Sj, then we could cover this new element. Well, assuming that it's in this set, with per element cost, well, at most the cost of the set divided by this number. Because we have so many uncovered elements, and that's the cost of the set, right? As easy as it can be. And since our algorithm chooses a set that's chooses the most cost-effective set, it can choose Sj or another one, but it can have at most this cost. So it chooses the set Sj star. And that means this alpha that we set here it can't be more than C of S J L minus I plus 1. Okay, fine. Now let's talk about the variables y. If we look at this variable that corresponds to the element that we now just are about to add, by definition we have this factor 1 over hn, the nth harmonic number. Well, and then this is the price. Price of u is just the alpha, so we just insert what we know about this. So far, so good. What we would like to show is that our set, this selection of variables y that the algorithm implicitly computes, is feasible for the dual. So consider the constraint for the set Sj that we now have in our mind. And if you look back, the constraints in the dual so we have to sum all elements in Sj, which means we can pull out, well, we would like to use this recurrence in any way. So all of these YUs, there's some way to write these as YEL1, YEI for some collection. We need another index I, another variable IM, because yeah, these must not come in the same order. They need not come in the same order. There can be another permutation. But we can still use this bound here for the worst cases, if you like. So we can first pull out these factors that are the same for all of these. And then to make this largest, we would like to have the smallest denominators here. And the smallest are just if these are the last elements that are added, so that I has the largest values. Then for the last element, this might be the last, so this is just 1. And that might be the second to last, up to 1 over L. That's the worst that can happen for these sets. And then this is just an HL divided by HN times the cost for this set. And since L is strictly less than, is less or equal than N, not necessarily strict, this is at most the cost. And well, this was exactly the constraint in the dual. So the dual constraint is satisfied. And since this holds for all sets, it's our selection Y. If we scale by this 1 over Hn, is in fact a feasible dual solution. And by this way, we can much more easily prove that this algorithm is an Hn approximation, because the cost of the solution that we return is just the sum of the prices and if we use these backwards, then that's Hn times the Yu. And now we use that this here is the dual objective function. So by weak duality, the dual objective is a lower bound for the primal objective. And this is what we called opt-frac, because it's the optimal solution, the optimal objective value for the fractional version of the ILP for set cover. And that's certainly a lower bound for op, because it just restricts the feasibility region a bit more. So by that we can prove that our good old greedy algorithm is an HN approximation, well, which we already knew, but we gained a bit more of an insight why exactly this was a good choice. Intuitively, it was just a natural idea to take this cost effectiveness as the measure according to which you order the sets and pick them greedily. But coming from the primal-dual perspective, it's actually a very natural way that you should assign the elements a certain price and then try to make this price fulfill this inequality. Coming up with the scaling of HN might be a bit tough, but in fact, if you look at this and just consider the worst case of an element that contains, of a set that contains all elements, then this must go up to HN. So it's clear that this is can be tied for a boring input where there's a set that covers all elements. Of course, this would not be a really interesting set cover instance. Now there's a bit more that we can read off from this because there's the important concept of an integrality gap, something I mentioned in the introductory part when we discussed vertex cover and matchings, where we found that using any inclusion maximal matching and then taking all endpoints of both endpoints of all matching edges gave us a vertex cover. Then we already discussed a bit the problem of the integrality gap, namely that in general we can't take just the maximal matching and hope for something better than a 2 approximation for vertex cover by that. So formally the integrality gap is defined like this. We take, so for the minimization problem, as for set cover, if you have a maximization problem, you would flip the 2. So the integrality gap is the optimal objective value of the integer version divided by the relaxation. And what we've seen for set cover is that this ratio can be up to HN, because we showed that there is a dual feasible solution that is HN away from a primal feasible solution. So we found 2 feasible solutions for the primal and the dual respectively, so that their distance in the objective function is at most HN. And we found that we could actually turn this into an algorithm, namely the greedy set cover algorithm. The question is whether we can improve upon that, and if there's a cleverer way to choose, say, the dual variables, cleverer than the way that we used it for the greedy version, so that we can improve this bound. So we would like to show a lower bound on this ratio. And in fact, we can show one that comes reasonably close, even though it's not exactly HN. What we can show is a certain value a little bit below HN. Here's the precise value, and this is what we actually show. So we show this part, and then here we just use that you can asymptotically have HN is asymptotically equivalent to the natural logarithm of n. Then you make a base change in the log, and you've this is asymptotic to 1, that's obvious. And then you get this result, and just that's the numerical value. So this result shows you that it's essentially not possible to improve the greedy algorithm by whatever clever scheme of rounding or by any LP relaxation based method. Because already the step of just dropping the integrality constraints in the LP, not saying how you would get an optimal solution to the fractional version and how to come back. Already this integrality constraint gives you such a step in the objective values. You can find a much better fractional cover than you can find in a real cover, an integral one. The construction that shows this is essentially an infinite family of counterexamples to something better. And for that, we assume that our universe size has a certain shape. So we have some fixed number L, so that our universe then is the numbers 1 to n. And we can, so this is isomorphic to, well, L-digit binary numbers, or L-bit binary numbers. And we will use, to just define the sets conveniently, this number representation, in that we view a number in U as a vector, I vector, which is essentially just the binary digits. Okay. So we use the binary representation of this number. And just for simplicity, we set the number n to 0. So if you like, you can use, well, formally you should first do modulo n and then take the binary representation of what you get. This is just for convenience. The order of these elements has no meaning, so this doesn't really make a difference. Now we have the sets Sj, which consist of all the numbers I, so that the I vector transposed the j vector, so the scalar product of the two, is 1 modulo 2. So if you compute everything modulo 2, that means, well, as an example, the scalar product of these two vectors would be first compute this boring example. So no, sorry, you first multiply the digits, and then you add up the digits modulo 1, 0, 1. So in the end, that's 1. Okay. Now this corresponds to the number 2. This corresponds to 1, 2, 3. That's 7, right? So that's what I showed in the example. And this is how we construct these sets for every j in our universe. So we have the same number of sets as we have elements, and we set the cost of all sets just to 1. Okay, now you can check that there's exactly n plus 1/2 such vectors that have a non-zero scalar product with the number in the index, with the j, but this is because of symmetries, the sets have all the same size. And also for every fixed number. The V again, that's the number of sets. So V is the sets that contain I, and their number is the same. It's also n plus 1/2. So each value I contained in n plus 2/2 sets. The point is that this is an extremely symmetric definition, because we use all L-bit binary words, we have the whole set available, and that gives you all these nice symmetries. So it's probably obvious that we will have the same size for all these sets and the same number of sets that contain any given value. That these two are also equal is something that you just find by computing it. So what this means first is if we set a fractional solution to exactly this, then this is a fractional set cover, meaning that it's a primally feasible solution, simply because we have so many sets that each element appears in, so we add up this times this, which is 1, and that's the primal constraint. And the cost of this fractional set cover is just n times this. And that's the first ingredient that we have down here. That's the same. Okay. Now the second step. For a real set cover, we will show that we need L sets at least to cover everything. And the way to show is assume that we have a smaller number of sets. So we have some I1 up to IP as sets, and we would like to show that their union misses at least one element in our set U. So we write a matrix that consists of the rows I1 vector up to IP vector. So this is a P times L matrix. Well, and since P is less than L, this matrix cannot have rank L because it doesn't have so many rows. The rank of this matrix can be at most P, so less than L. But since the underlying vector space here of the I vectors is has dimension L, that's the number of entries, and well, this needs a bit of algebra. Computing modulo 2, that means we're using the field Z2, and the integers modulo 2. That means that these vector spaces have the full dimension. So the null space of A is thus not just the 0 vector, but there is another number j, so that aj vector is 0, which is just the definition of the null space. Well, that means since this is the scalar product of the vector with any of these rows is 0, so 0 is also the vector if you like, That means J is not contained in any of these. So these are not a cover. And that means we have at least opt is at least L. Right? We need at least L sets because less than L don't suffice. And then, well, what is L? Just by definition, we defined n to be 2 to the L minus 1. So if you invert that, you find exactly what we claimed here. And that completes the proof. So what this means is that there's an integrality gap that's at the very heart of the set cover integer linear program of essentially this logarithmic size that you can't overcome. There are instances where you achieve that. And I guess with a more contrived example, you can show that this is essentially optimal, even though this might be beyond what we would like to prove in this course. So there's a natural limit to the approximation guarantee we can reach by our methods that we've seen so far for set cover. Of course, this does not exclude the possibility of an entirely different idea to prove a much better approximation for set cover. But it shows that it's unlikely and that we don't have to continue searching based on linear programs. We will not be the logarithmic approximation factor. Okay. What we've seen up to now, based on linear programming arguments, was a new justification for methods that we already had, like the greedy algorithm we've just discussed. And we had another family of algorithms that were based on first solving the LP to optimality, which is, as I mentioned in the beginning of the session, quite expensive in practice compared to the simple greedy method. And then rounding the result appropriately, giving you essentially the same guarantees. But it feels like the real benefit of LPs has not yet shown. And in fact, we can make much more direct use of this primal-dual idea that we've discussed on LPs than what we've seen so far. And in that sense, combine these two things, produce new methods that do not need to solve an LP to optimality. And the idea is we start with two solutions, namely for the primal and for the dual. And for a beginning, we can just pick some solutions where we can easily show that they're feasible, but we know they're essentially very bad, far away from optimal. And then, iteratively update the solutions to match more of the complementary slackness conditions. We'll see in a second that really the complementary slackness conditions give us exact pointers how we should change our current solution candidates so that they improve. If we can do this until all are satisfied exactly, we get an optimal solution. So this is very good, but we will usually not be able to do so. So for hard problems, this will not work. So we should instead relax the conditions a bit. So but in a sense that x remains always feasible and integral, so that we can use the solution that we compute at any point in time to give a real solution to our original problem, which is an integer program. But for y, we only require a relaxed form of the complementary slackness conditions, so that in the end we will not have an optimal solution, but still any feasible y gives us a bound on the optimal solution, so we can compare what we get with x and what we know is not possible to achieve or not possible to exceed by y. Okay, that's the abstract idea. Now for set cover, the complementary slackness conditions look like this. Remember, the complementary slackness conditions always say either one of the variables in the primal or in the dual are 0, so tight in terms of the non-negativity constraint, weakly positivity constraint, or the constraint for this variable, which is in the dual of the problem, is fulfilled with equality. And these are just the two kind of constraints that we have. The dual constraints said that the value that we assign to the elements in the universe summed up over all elements in one of the subsets must exactly represent the cost of this set. And these were the primal constraints. If we sum up all variables for the sets that contain a certain value u, we should have at least one, or in the equality part, exactly one. So we cover everything. So this is important. We should not play with that one. But this is not really required, so we can relax that. So we know that by strong duality, we will have solutions that fulfill both of these simultaneously, but no integral ones in general. So we relax the dual constraints. So that we don't, relax the dual complementary slackness conditions, I would say. So that here we don't require exactly 1, but we require at most f, which is essentially requiring nothing, because this is always fulfilled. We essentially drop this part, because f was the global frequency. That's the number of sets that, the maximum number of sets that any given u appears in. So this is a vacuous condition. Okay. And the interesting part will be to show that we still retain a feasible solution. Essentially because whenever we don't select one of the subsets, we require that there's an equality here, so that we distribute the cost of this, that this set would have, to the values that we already have assigned to our elements in the universe. Well, and whenever these are non-zero, we require, well, nothing in that case. Now, how can we turn this into an algorithm? So the idea how to make this is first, we select some yu where this is not fulfilled, and we increase it until this becomes fulfilled for one of the sets. So let's say this is CSC1, this is CSC2, so we increase the value here until we fulfill this constraint, but we only consider the sets that we are currently so this only becomes active if we actually select a set. And if this is then fulfilled with equality, we no longer need this. So, okay, we require this condition always to hold. So for all sets where this is not yet satisfied, we must have xj equals 0 at this time. Sorry for the confusion. So we increase yu for all sets that we currently have not selected. So where currently xj is 1. And now, since now the right-hand side is fulfilled, we don't have to fulfill the left-hand side. So we set this xj to 1, which means we pick one of the new sets. And essentially to do that, we just compute this difference, so this minus the left-hand side. So we have to find the set J where this is minimal. But we exclude all the sets where it's already exactly 0. So if you write this down as an algorithm in a very abstract setting, in a very abstract language, admittedly, it looks like this. The primal-dual set cover gets a set cover instance. It computes the global frequency. It starts with two solutions that are just all 0, where this is for the primal problem. This is not yet feasible, but for the dual, it is. Because if you go back one more time, what the two require is just here, if we set everything to 0, this is fulfilled trivially. Whereas here, we're violating all these constraints. So I think I said here, start with 2 feasible solutions is not quite accurate. I think we should say we start with any 2 solutions. And we would like that the dual is feasible, whereas the primal is infeasible but integral. And then we update the solutions to match more of the CSC conditions until the primal is feasible. And we always keep the dual feasible so that we always have a bound on how good we can ever get. And that's how it works. And by relaxing the conditions a bit, we stop a bit earlier than we would actually do normally, because we can't jump over the integrality gap. So here's what we do for the set cover. We start with this all 0 solutions, where this is certainly feasible, and this is a very good solution. It's just not solving the problem. I mean, the cost of x all 0 would be great. Now we choose for all the elements that we have not yet covered. So here I use it the other way around just because it's more convenient. We have T, the set of all elements initially. And while this is not empty, we choose one element that we have to cover still. Then we consider its variable and increase it by the amount that we have here. So we essentially compute the argmin j of these. So that this is for all the sets that we have not picked yet. And then we increase the yu until this is tight for one of the sets. So essentially we compute the argmin and then add the min to yu, and then we know by the argmin already which set it was, but maybe it's easier to write it like this. So we compute this delta and then essentially set yu plus delta. Okay, and then here in the simple formulation where you don't use the argmin, you just iterate over all the sets and check if they now fulfill this with equality. And for all that do, we see that that's a T. So we remove from T all the elements in that set because we now cover that one. We now take it up into cover, and we do so by setting xj to 1. And then in the end, what we return is all the sets where xj is 1. So essentially, we store the solution in a bit vector representation, right? So this is a very simple algorithm in terms of running time, because all it has to do is to compute these differences and so on in this minima in a loop, but it doesn't have to solve the LPs, even though it is actually based on constructing solutions for the primal and the dual problem, right? And it stops, as you see, the second half, this one is never really checked because this is a vacuous condition. It's always fulfilled. The only one that we actually used in the end was this one. And this is, so to say, the little downside of the primal dual approach. It does give you a nudge, a hint where, in what direction to improve your solutions. But there's always a little problem-specific step left before you have the final algorithm. What it gives you for this is usually a very efficient method in the end. Okay, and what's missing is the approximation guarantee for this method. And we can show that this is again an F approximation for the set cover problem. So again, we have these two approximation ratios that we had initially. The dual fitting approach, where we had the scaled Y solution, gave us an HN approximation, and the primal-dual approach in this formulation gives us an F approximation. So let's see how we can prove this. The solution that we return, first thing we should show is that this is a set cover at all. But that's just by construction. We only remove elements from T, the to-do set of elements still to be covered. We only remove elements from T when we also set the variable here to 1. So that means we include only elements that we actually cover in the solution. So once we return something, we make sure that we have everything covered. So this is just by definition. And this also means that this solution that we construct here, the primal solution, is actually feasible also for the LP, right? Also, for all the sets where we set xj to 1, we had at this point in time this equality. So for all the sets that are selected in the cover, we have that the corresponding part of the dual solution corresponds exactly to the cost of this set. It's clear at this point in time, and notice that we only increase values. But we never decrease them. And in fact, once we have selected a set for a certain element u that contains a certain element u, this element is removed from T, so we will never touch any of the values yu for a set that's covered. So this holds when xj was set to 1 and all yu for these elements in the set, they are never touched again. So it still holds when we finish. Okay. This means if we sum over all the sets and sum up their costs times xj, so this is the value of the cost of our solution. Well, we can write this as cost of C, the solution that we computed. Then here, either xj is 0, then the term here is not really in the sum. Or if xj is 1, then we know by the complementary slackness conditions part 1 here that this holds. And in fact, we just argued that we satisfy this complementary slackness conditions part 1. So we can just give that label here again. Then by C is C1, we can write here this sum yu. Now we can, these are finite sums, we can move this in and exchange summation. So we first sum over all elements in the universe, and then yu, and how often does this occur? Well, all elements, now we sum over all j in V of u, namely all the sets where the u occurred. So how often do we have a certain yu? Well, for all the sets that contain this, and then we have here the xj. Now we can bound this one by f, because that's the definition of the frequency. We know that this, because that's an, so, well, we know V of u is less than or equal to f just by definition, and all these are at most 1. So we have an f here, and then we can pull out. And now we recognize that this is the dual objective. And recall that we always maintain y as a feasible solution. We make sure that we never increase y larger than this. So because y is feasible, and by weak duality, we can bound this by the optimal fraction, by the optimal value of the relaxed set cover LP, which is just opt frag. Well, and this is an upper bound. This is upper bounded by the optimal version of the integer version. And so, what we compute, the solution has at most f times opt cost, so it's an f approximation. Okay. This concludes the part on LP approximations and LP duality. You look at one more example in the exercises. I think it's a very nice part of the theory, because often it's easy to write down just an LP for some problem, and dualizing it and trying to make sense of what intuitively the dual means often leads to an idea how to construct a nice algorithm. Now for the rest of the course, we will look at a bit of the complexity theoretic side of approximation algorithms. I moved this to the end of the chapter because the result in the end, the inapproximability results, are among the most deep results that we will touch on. We will not, a central theorem in that part we will not prove, because that would fill an entire lecture on its own. But still it's intriguing, the connections that you can draw in this point. And for today we will just start with a few definitions so that we can have a running start next time. So the first part will be about what actually is a class of good approximations, or a class of problems for which we have good approximations. The definition goes as follows. The long-term goal is prove some problems inapproximable in a certain sense. So we first need to define what approximability actually should mean. Up to now, we considered specific problems and concrete algorithms, and then we computed their approximation ratio. For a round theory, we will have to boil this down to a single definition in a sense. What we'll define here is two terms, PTAS and FPTAS, abbreviated because the full name is a bit long. We start with an optimization problem as usual. Now an algorithm is algorithm A is a polynomial time approximation scheme for this problem if A given an instance of the problem and some parameter epsilon computes a solution that's feasible and is at most a 1 plus epsilon factor worse than the optimum. And it should need polynomial time in X. So FPTAS means we have not just a single approximation algorithm, but we have a parameterized approximation algorithm that we can give a desired relative error, and then it should just compute a solution that has this kind of guarantee. And we would like this to be possible for any epsilon. So that means that this is approximable to any desired relative error, which is quite strong an assumption. But the polynomial time here is only with respect to X and totally ignoring the epsilon, which means that we can have running times like this, where the exponent is exponential in 1 over epsilon. So if we want to make epsilon reasonably small, reasonably close to 0, this will completely explode, and we will not have something that's usable in practice. Therefore, what you would like to have in practice is actually an FPTAS, a fully polynomial time approximation scheme. And there we require, in addition to what the PTAS is, we require that the running time is polynomial in the length of the input and 1 over epsilon. So that when you make epsilon go to 0, you do allow a larger running time, but only in a moderate sense. Okay, so you can have 1 over epsilon to a fixed constant, a polynomial in this. That's fine, but not up to an arbitrary degree depending on epsilon. And even though so let's say in practice we would like to have an FPTAS, because really the running time guarantee of a PTAS doesn't help us a lot. However, even requiring a PTAS is actually quite a lot, because only a few problems have PTAS. We will see an example next time, and some more connections to other complexity theoretic concepts that we've already discussed. So we will be a bit more modest and say the class APX is the set of all problems that have at least some constant factor approximation algorithm. So this is maybe a bit, so I should say this is there exists a fixed C that only depends on the problem, so that there is a C-approx algorithm for this, for U, that runs in poly time. Okay, that's the class of problems that we will consider as easily approximable, even though the constant might be large. But it already separates, so we've already seen that vertex cover is in APX, because we know how to do a 2 approximation. And we know also that vertex cover is apparently one of the problems that are, well, NP hard, but not as hard as many other problems. Whereas for the set cover problem, we have not seen anything that comes even close to a constant factor approximation. So we would conjecture that it's actually not in APX. Well, as usually in the theoretical, in the complexity theory realm, we will not be able to prove this because it boils down to the question of P is equal or not to NP. But we will have a clear separation in terms of the complexity of the problems as we had it before. And so set cover would be one of the problems where we expect to be able to show, at least conditionally on some complexity of the theoretic assumptions, that it's not in APX. So I think it makes a sensible cut between the two realms. And we will discuss more on that next time.